Hi, last video we explained how to find the energy and power for continuous time signals. In this video we are going to explain how to do the same thing for discrete time signals. The formula are very similar except we are just not using integration because it's sequence. So we are using summation. So to find the energy of a signal, discrete time signal or sequence, you square the signal itself, the magnitude of the signal, and then instead of integrating from negative infinity to infinity, you will find the summation from n equal to negative infinity to n equal to positive infinity, and you find the energy. The power will be the same thing. You are making the summation from negative n to positive n and divided by 1 over 2n plus 1. You might ask why I'm dividing by 2n plus 1, not 2n, because it's from negative n to positive n. Out it is simply just let's take n is equal to 3. So you have 0, you have 1, you have 2, you have 3. You have on the other side negative 1, negative 2, and negative 3. When you calculate here, you find that's negative 1, negative 2, negative 3, that's 3. From 1 to 3, that's another 3. And there is 1 in the middle at 0, n equals 0, that's the 1. That's why we divide by 1 over 2n plus 1. And then the limit when n goes to infinity. Again, we have a special expression to calculate the average power for periodic signal will be 1 over n naught, which n naught is the period of the sequence, and the summation from any number up to this number wearing n naught minus 1 for the square value of the signal itself. So after you've calculated the energy and power, you do the same rule we use with continuous time signal. If the energy is finite, has a finite value, it's an energy signal. If the power has a finite value, it's a power signal. And if energy and power, they do not, or they are not finite, then it's neither power or energy signal. Exactly the same thing we applied for continuous time signal. So just let's go ahead and take some example. But before we take the example, it's very important we are dealing with summation. So you got to review some rules for how to find the sum of geometric series, if it's infinite or finite. But just I'm going to post it on the folio, but I'm going to use whatever I need now when I start solving the problem, not to confuse you. We have here 3 different problems in this example. We need to decide if the signal, if the discrete time signal here or the sequence, is it power, energy signal, or neither. I'll take the first one. X of n is equal e power minus 0.5n when n greater to 0, and 0 when n less than 0. So it's defined for n greater than 0 or equal 0. The first thing you do, you will say x of n, the magnitude, there's no imaginary part, so it's just to be the same thing, which is equal to e to the power minus 0.5n. And then you square this value, you square this value. When you find the square value will be e minus, and 2 times 0.5 would be 1, so that's square value of x, or x squared. All right, to find the energy, we are going to find the summation from n equal negative infinity to positive infinity to e power minus n. Remember, now I have to mention something here. In geometric series, all right, here, if you want to sum r power n in minus infinity to infinity, it will be approximately equal to 1 over 1 minus r, given that the magnitude of r is less than 1 fraction. So r power n, I try to do that r power n. So how you do that? If you take this in out, so what's r will be e power minus 1, right? Okay, so is it e power negative 1 is greater than 1, less than 1? Actually, it's fraction. If you do it in the calculator, you can find it's equal to 0.368. So just you can write it 0.368 power n. Okay, so the energy is equal to the sum of this e power minus n, which is equal to 0.368 power n. And since this is your r and less than 1, will be equal to 1 over 1 minus r, 0.368. 368, which will be equal to 1.582. Well, so the energy is a value, it is infinity. So you can say this signal is an energy signal. Okay. The second example here, we have a sequence that's equal to 0 when n less than 0 and equal to 1 when n greater. So we can say that x of n, according to this graph, is equal to 1 when n greater than or equal 0, otherwise is equal to 0. Okay, let's, it looks like it can be power and it can be energy, it can be neither. So what we'll do, well, if you try the energy, will be the integration from minus infinity to infinity and the square, but I mean, because I mean you start from 0, you can write from 0 now, all right, and the value 1 is going to be 1 dt will be t, and you from 0 to infinity will be infinity. So it's not energy. So let's try, maybe it's power. The power formula, or the average power, is equal to limit n goes to infinity 1 over 2n plus 1 summation from n, you pick any number, I can pick 0 now, up to I don't know, you shouldn't start from 0, from minus n. The formula says from minus n to positive n x n square. Okay, that's the formula for the average power, and I'm going to apply now n infinity 1 over 2n plus 1, and now I start to substitute. I don't have negative n, I have 0, I put 0 up to n. Okay, and the value is equal 1. So now we need to know the summation of 1 from 0 to n. There is a formula for it, I put it there. When you're adding 1 from 0 to n is equal n plus 1. So you will have this one, n plus 1. So I'll write L limit n goes to infinity 1 over 2n plus 1, and the summation of 1 is equal n plus 1. So will be equal to the limit n goes to infinity n plus 1 to n plus 1. And you know, when you find the limit of the infinity, you take the highest order, and the highest order, look at the coefficient. The coefficient of this one is equal to 1. The coefficient of the highest order term here is 2. So it will be equal 1 over 2. So the power is equal to half, which is less than infinity. So you can say it is a power signal in this example. That's great. Well, the last example here for the discrete time signal is given in the graph. That's x of n given here. When you look at it, you can see it's periodic. It starts from n0, and then it will finish at n equals 6 and be repeated again. And even before that, you'll find it's the same pattern repeated. So the period from 0 to 6. So you can say that n naught, the period, is equal to 6, and the value of xn is equal to 1, but it's equal to 1 from 0 to 3, right? That's here 3. So it's 1 when n between 0 and 3, and then 0 in the rest of the period. The period is equal to 6. So let's just do that. I will just go to a new page. How can you find the power for periodic? Now you ask again, why you don't write the energy formula? Because the periodic signal usually is power signal. So I try to try my luck and see if it's going to work. For periodic signal, the average power formula is defined like that. Power equal to 1 over n naught, the period, the summation from over one period, like from 0 to n naught, and x in magnitude square. Okay, we know that the period is equal to 6. We found it's equal to 6, and n equals 0. It should be to 6, but I will show you the graph here. It's 0 after 3, so it's from 0 to 3. So from 0 to 3, and the function is equal 1, it's going to be equal 1. All right, so it'll be 1 over 6. The summation we did that before will equal n plus 1, so you have 3 plus 1 will be equal 4. Okay, maybe I said fast. The summation from n equal to 0 to n capital to 1 is equal n plus 1. In this case, n is equal 3, so it'll be 3 plus 1 equal 4. 4 over 6, 2 over 3. Yes, it's less than infinity. Again, it's a power signal. By this example, we're done with the energy and power signals for discrete time signals.